So next one is microwave filters. Filters are circuits which are going to allow or reject a particular band of frequency. So they are two-port reciprocal passive networks which will attenuate unwanted signal frequencies while they allow only a selected band of wanted frequencies. So definitely filters we'll be using, yeah, R, L, and C for designing the filters. And there are three types of filters. One is reflective filter, which has L and C. Next one is absorptive filters, which will dissipate the unwanted signal internally and pass the wanted signal. Last one is a lossy filter, which will heavily attenuate the rejected signal and the low loss the wanted signal. So three types of filter configurations are available. And since we are going to operate at a very high frequency, the impedance matching should be confined to 50 ohms or 75 ohms, where majority of the microwave circuits are going to operate. So mostly I'm going to use L and C networks and I'm going to terminate them with Z0. So the different parameters are there for filter. You have pass bandwidth, you have stop band frequencies, input output impedance, return loss, insertion loss, and group delay. So these are different parameters of filters. This is a general diagram. You have a source, you have a filter, and you have a load. So input power from generator will go to the filter. Some reflected power will go back. The effective power will be going to the load. So you have parameters like insertion loss. Insertion loss is what is the total power entering your circuit divided by the power loss happening. So Pi by PL. Return loss is how much power is incoming, getting in, and how much power is reflected back. Pi by PR. And time delay is going to be 1 by 2 pi into a variation of the phase angle with respect to frequency. Phi t is the transmission phase angle, df is the frequency. So group delay. So I can find the insertion loss, return loss, and group delay using these three formulas. And four types of filters, low pass, high pass, band stop, and band pass. Low pass, first one is a high pass filter. So low frequencies have zero gain and it allows the high frequencies. Next, second type you see low frequencies are allowed and slowly blocks the high frequency. Third one is band stop. It does not allow a band of frequency to pass through. Next one is band pass, which is reverse of this. It allows only a band of frequencies and rejects all other frequencies outside this band. So majority we have these four types of filters: low pass, high pass, band pass, and band stop filters. When you conventionally use circuits, you'll be using discrete components L and C. But when you use microwave circuits, I cannot go for L and C. I'll be using these structures. So when it is a shunt L, I'll be using this structure to create a shunt L effect. When it is going to be shunt C, I'll be using this structure to create a shunt capacitor effect. When I'm going to use a series L, I'll be using this structure to create the series inductor effect. When I'm going to have a series capacitor, I'm going to use this structure to create the series capacitance effect. So you have for coaxial cable they have given, for microstrip they have given, and conventional thing also they have given the three diagrams for each of the cases. So depending on what frequency you are going to operate and what components you are going to use, you can replace that particular component with each of the below structures to have the necessary effect of L and C. In microwave filters, lumped elements are simulated by means of waveguides. So we don't use conventional RLC here. We are going to use waveguides. Okay, so that's what is shown here. The shunt inductance raised by means of a short circuit step less than lambda by 4. That's what we have seen in that graph. And the shunt capacitance greater than lambda by 4. Both are opposite. Series inductance less than lambda by 4. Shunt capacitance more than lambda by 4.